Exercise 29 next, subfield test. Here we are given a field F and a subset K of F which has at least two elements in it. Also, these conditions are true, that is, if we consider any two elements A and B in K where B is non-zero, the difference A minus B and the product AB inverse as you would calculate them in the field F, they actually belong to K. Now under these conditions we have to prove that K is a subfield of F. That means K itself is a field if we restrict the operations on F on K. That is the addition and multiplication that we have in F, if we restrict those things on K, then K itself becomes a field. That's what we have to show. So let's see the solution. Now we start off by observing that K has at least two elements. This hypothesis we will not fully use it right now itself. Right now the only thing we need right now is that K is a non-empty subset of F. If it has at least two elements, then of course it has something. So we start the solution like that. Note that K is a non-empty subset of F. Now we are going to show that K is a subfield of F. So we first attack the operation of addition. So let A and B be any two elements in K. If B is not equal to, we don't really know what B is. Okay, B may be non-zero, B may be zero also, and accordingly two cases will now arise. So if B is non-zero, we are assuming this one first because this is the case where we have a ready-made hypothesis for us. Then by the hypothesis A minus B is in K. On the other hand, if B is equal to 0, then A minus B is just simply A, and which of course is in K. So we see that no matter what the case is, A minus B, if A and B are coming from K, then their difference A minus B is always in K. Hence, by the subgroup test that we already have seen in group theory, K is a subgroup of F under addition. So in showing that K is a field, the job is almost half done, because this final line here tells us that K is now an abelian group under the addition operation that we have in F. Is a subgroup of F under addition. Okay, now next we have to look at multiplication. Now this is where that hypothesis will come into play fully, that K has at least two elements. So we write next, since K has at least two elements, K difference 0 is a non-empty subset of F difference 0. That is because even on removal of 0, there is still something else in K, because at least 2, and this of course is a subset of this, so now it becomes a non-empty subset of this. Now next what we do, we take A and B to be any two elements, this time in K difference 0. Then by the hypothesis, A B inverse belongs to K. So this is that other part of the hypothesis which talks about the product product of A and B inverse. You note one thing, that actually this is a special case of what is given in the exercise. That's because in the exercise we need only B to be non-zero. Here however A is also non-zero, but that does not affect anything. So still AB inverse belongs to K. So again you can use the subgroup test and now claim that this set is a subgroup of this set under multiplication. So hence K difference 0 is a subgroup of F difference 0 under multiplication. And in the background of this thing, we of course have the fact that F difference 0 is a group under multiplication, and that is coming from the hypothesis that F is a field. So the non-zero elements in it will form a group under multiplication, and not just that, that group is abelian. The multiplication operation is commutative. This under multiplication. Okay, but where are we heading with these things? We have shown that this is an abelian group because we have shown that this is a subgroup of this group, and just now we have shown that this is a subgroup of this group. But our aim is to show that K is a subfield of F. That means K is a field under this addition and multiplication that we have in F. So what is it that we have achieved so far? We have in fact so far just shown that the subgroup structure is there. However, we will just go directly. Okay, so let us just recall what the definition of a field is. A field is a commutative ring with unity in which every non-zero element has a multiplicative inverse. That is, every non-zero element has has an inverse under the operation multiplication. Okay, but we need to show that it's a commutative ring first, and that too with unity. And in that we have in fact done half the work. So now let us see. Now we are going to use this thing that we have concluded here. Next, let A and B belong to K. So now our aim is to show that K is first of all a ring under these operations. Now you may have observed one thing, that we are again and again taking A and B in K. You should understand that these are just general variable elements. Whatever A and B we, for example, take here, you should not think that they are the same thing. They are just variables. They are not fixed elements. If you feel somewhat uncomfortable using the same symbol, you can use C and D and some other things also. Okay. So now first of all, what we want to show is that if you take the product of A and B, that is AB, then that belongs to K. If at least one of A or B is 0, then AB is 0, and this is coming from the fact that we are after all in the field F. So if at least one of A or B is 0, then AB will clearly be 0, and that itself is coming from the fact that a field itself is a ring. So from elementary properties of rings, you are having this. However, you have already shown that K is a group under addition. So the additive identity, that means the 0 element in F, is already there in K. So that's why this belongs to K. However, if both A and B are non-zero, on the other hand, if both A and B are non-zero, then also their product belongs to K, and this fact is coming from here. We are claiming, we are concluding that this is a subgroup of this under multiplication, so this will be closed under multiplication also. If A, B are both non-zero, then they belong to this, and hence their product also belongs to this, that is, ultimately their product belongs to K. So K, besides being an abelian group under addition, now has become closed under multiplication in general, okay, for any two elements A and B in K. What else is true? Multiplication is associative all throughout F. So in particular, if you focus your attention on K, there also it is associative. Is associative in K, since it's associative in F. This kind of things, some axioms which are true in the large systems, though it's also true in on any subset, we will write this kind of things the first few times, but as we become more and more familiar with these things, we will stop writing these things. And things which you just don't have to do anything for them, you just write a line for them. That kind of things we will not always write in K, and hence in particular in what have I written? Particularly associative in F, and hence in particular in K as well. The unity 1 is different from 0, and this fact of course is coming from the fact that in any field, in fact in any ring also, in this book, whenever there is a unity in the ring, it is by definition different from 0. It's a non-zero element. So the unity is different from 0. Okay, do I really need to mention this fact? Can I not just directly write that the unity belongs to, oh no, I need to mention this fact, is different from 0, and hence this belongs to K. You probably will not understand the reason for this if I just simply write like this. I should elaborate a bit more. Like this is, instead of writing this, let me write like this. The unity 1 is the identity element in the group this under multiplication. This we already know. Hence, it will also belong to K minus 0. Why? Because we have we already concluded that this is a subgroup of this under multiplication. So it must contain the identity element of that group, which is 1. So from there we are getting the fact that 1 belongs to K. Okay. So we have seen that K is closed under multiplication. Multiplication is associative. The unit element also belongs to, the unity also belongs to K. And what else? The distributive law. Yeah. The two distributive laws. It's they are also true in K because they are true in F. So it's somewhat like associativity. Laws are true in F, and so in particular they are also true in K. That means here we have shown that K is a ring under the addition and multiplication that we have in F, and because the multiplication is coming from a field, it is commutative. So that means this is a commutative ring, and that too with unity. So we can just simply now directly write, hence K is a commutative ring under the operations in F. Here itself I should have written with unity. Under the operations in F. Next, let A be a non-zero element in K. Then A is an element in this group under multiplication, so its inverse will exist, and that too in the group itself. And so A inverse belongs to this, i.e. ultimately it belongs to K. That means not only have we shown that K is a commutative ring with unity under the operations in F, but we have also shown that any non-zero element in K has a multiplicative inverse that is also in K. So by definition, K is a field, and since the operations are coming from F, K is a subfield of F. So this is our subfield test. And now we can conveniently use this to show that some such subset of a field is a subfield. And it can be used to sometimes show that a system is a field, because if you just simply use the definition of a field all the time, every time you need to show that something is a field, you just show that it's a commutative ring with unity in which this and that happen, then it becomes long, and there is in fact no need to do that, because in most of the instances of fields that we will encounter in this book, at least, they are subfields of some known field. So it's much easier to apply the subfield test, and much quicker also. And such is the next one, I think. Yes. The next one is exercise 30. Let D be a positive integer. Prove that this field, excuse me, Q root D. Sorry, I said this field, this set where the elements look like this and where A and B belong. You understand that this Q is denoting the field of rational numbers. This set is a field. Now if something like this is simply given, then it's meaningless. But we know from context what the author is trying to say here. That means actually, although we just simply see a set, but definitely he requires us to show that this is a field under ordinary addition and multiplication of, you can say, real numbers, because after all these are real numbers. And that is why it's instead of just simply using the definition of a field and verify all the axioms, we can show that this is a subfield of R, and that's what we are going to do, because now we have the subfield test. So what we will do, let's just start the solution by mentioning that we show that this is a subfield of the field of real numbers. And before that, let me just refill. I think I am losing ink. Okay, so that means what is it that we have to do? We have to again take A and B, two elements in this set, and where B is non-zero, such that A minus B and AB inverse, they both belong to this. However, keep in mind that here also all the conditions from the subfield test should be true. All the hypotheses should be there. You have to also show that this subset of R is having at least two elements. So that thing should also be there, which however is rather easy. Note that see what, I'm a little absent-minded today. Already I have written solution and again I am writing solution. Sorry about that. Is a subfield of R. Note that and 1 equal to 1 plus 0 root D belong to our set. Okay. Now we cannot just simply write A and B. We have to write the proper form of the elements. So let us write A1 plus B1 root D and A2 plus B2 root D in the set where A2 plus B2 root D is not equal to 0. Now we need to simplify this condition, or rather I should say we need to write a consequence that immediately comes from this consideration, that from the non-zero-ness of this element. If we suppose that okay, oh, this is not 0, this is non-zero, right? Oh, so okay, so I was thinking about something else. I'm not really in tune today. If it was 0, then A2 and B2 should have both been 0. However, it is given non-zero. Anyway, so let us just start our job. Then, first we look at the difference of these two things. A1 plus B1 root D minus A2 plus B2 root D equal to what? Equals A1 minus A2 plus B1 minus B2 root D, and this belongs to our set. What is the reason for this? That is because A1, B1, A2, B2, these are rational numbers, simply because that type of things are there in this set. So their differences are also rational numbers, and that is why this is again in Q root D. And what about this? They actually mean the same thing. We haven't done anything new here. We are just writing it in a different manner. But this manner, because it's more familiar to us, or rather, we know what we need to do after this. We need to rationalize the denominator, if you know what I mean. That means but there is a, if we just simply continue the calculation like this, there will be a gap. What is that gap? Note that we have multiplied and divided by this real number. Is it non-zero? That we need to ascertain, because without knowing that, this may be wrong. However, it actually is non-zero, and the non-zeroness of this comes from this condition that this is non-zero. I am not going to, what I am going to do is that I will leave it out. I won't do that. I leave it to you to show that non-zeroness of A2 plus B2 root D implies A2 minus B2 root D is also non-zero. let me just see if we can figure it out, and we continue our calculation. So now if we perform the multiplication, what shall we get? A1 A2 plus, let me see these two also. Well, we won't have plus, minus B1 B2 times square of root D, because root D is because after all D is a positive, what is given, is it a positive rational number or positive integer? A positive integer. Anyway, it is positive, it's a positive real number, so squaring it we would get just D plus, now the cross terms, B1 A2 root D minus A1 B2 times root, I'm writing it here, okay, you understand. And this is of course A square minus B square, so here we will have A2 square minus B2 square times root D square, that means D B2 square. And once you know, once you are able to show that this is non-zero, you don't have to worry about this being non-zero or not. It will be non-zero, because this is non-zero, and once you show that this is also non-zero, their product, which is this, is non-zero. Okay, now the final step in this calculation, we can write this entire thing like this: A1 A2 minus B1 B2 D plus B1 A2 minus A1 B2 divided by A2 square minus D B2 square times square root of D. Now because these A1, A2, B1, B2, these are all rational numbers, D of course is also a rational number, being itself a positive integer, and the denominators are, there is only one denominator, of course, that is also a non-zero rational number. So these two quotients are actually rational numbers, and that is why this again belongs to this. So by the subfield test, well, if you want to treat it as a name of that test, you should use capital letters. By the subfield test, this is a subfield of R, and hence a field in its own right. And we will solve another one, and then we will call it a night. But before we go to the next one, you just notice one thing, that if that D turns out to be a positive perfect square number, then this subfield q root t actually coincides with q. It reduces to q itself. Exactly how, that I leave to you to understand. And our solution is over here. So let's see the next one. Let R be a ring with unity 1 if the product of any pair of non-zero elements of R is again non-zero. Prove that AB equal to 1 implies BA equal to 1. So that means what is it that we have to show here? We are given a ring R with unity such that if you multiply any two non-zero elements in the ring, then the result is also a non-zero element. You have to prove that if A and B are two elements in the ring whose product is the unity 1, then BA is also equal to 1. Now this exercise becomes trivial if R is a commutative ring, which however of course is not given, so we cannot assume anything about commutativity. The solution is rather easy. However, we write systematically. Let A and B be elements in R such that AB is equal to 1. Because the unity by definition is not equal to 0, so both A and B must be non-zero. So we won't really need the non-zeroness of B, but the non-zeroness of A is what we will need. So next we write, since 1 is not equal to 0, A is not equal to 0. Now ABA, if you multiply on both sides from the right side by A, you get ABA equal to A. Hence ABA minus A is equal to 0, and we can in fact do the entire calculation that comes next in one line. So from the previous equation, we get 0 equal to ABA minus A. Now using the left distributive law that is there in the ring, you can take A common out in such a way that you have BA minus 1. That you can do. So now note that you have a product of two elements in the ring. One of them is A and the other is BA minus 1, and that product is equal to 0, and it's already given that A is non-zero. Now if BA minus 1 also is non-zero, then by our hypothesis that the product of a pair of non-zero elements is non-zero, this should have been non-zero. However, it is not. So that means this cannot be non-zero, it has to be equal to 0. Thus, we must have BA minus 1 equal to 0, i.e. BA equal to 1. So that's how, in spite of maybe having commutativity or not having commutativity, whatever the case is, if AB is 1, then BA also becomes 1, provided these conditions are true. And with that, let's just end things here itself today. Tomorrow we have analysis. So until then, this is me, Lucifer, from a mathematical room. Have a nice night.